Okay, hello. This is ACT Science Video 402. If you haven't already, take your time to look at video 401. It's about 15 minutes long and it just goes through the how-to on the science section. This 402 video, we're going to look at two passages. We're going to look at as I covered in the previous video, 5 out of 6 of the passages are just kind of looking at experiments and being able to diagnose your inputs, which are your independent variables, and then your outputs, which are your dependent variables and how they're related, and being able to understand the relationship kind of just briefly through the chart. So what we'll do here is we'll look at passages 1 and 2 from this test. This test, you have it. It's April 2014. It's the course materials test 1. Feel free to even try passages 1 and 2 on your own and then reference this video afterwards so that you can compare kind of how you did it to the review in this video. But course materials test 1. Okay, so as always, you have a little under 6 minutes per passage. Typically, you'll take about a minute to a minute and a half just canvassing what's the background information, what are my inputs, what are my outputs. Obviously, as we go through it on this video, it will take longer than a minute to a minute and a half, so just take that with a grain of salt. And then you would take the last 5 minutes to answer the question. So it's about 1 minute to kind of review the material, and then roughly 5 minutes for the questions. And that is a 5. I know that looks a little weird, but yeah, 5 minutes for the questions. Okay, so let's just get right to it. Let's figure out kind of what's going on, what are inputs and what are outputs. Passage 1. Two measures of water quality are the number of E. coli bacteria present and the biotic index, or BI, a numerical value based on the type, diversity, and pollution tolerance of aquatic invertebrate animals. Both of these measures can be affected by water flow. Okay, so we know that measuring the amount of bacteria in the water tells us kind of the water quality. And then we also know that measuring the biotic index, which is based off of the number of different factors, all in brackets, also gives us an indication of water quality. So that's what we should pull from that. E. coli levels are about, and then also just that water flow plays a role as well. E. coli levels that are above 100 colonies formed per 100 milliliters of water indicate reduced water quality. So just to make a quick note, if you go above 100 on the measurement, it's reduced water quality. Figure 1 shows E. coli levels on 5 collection days at sites 1 and 2 in a river. So really simple. The x-axis is our input, okay? So we input a day and we also input a site. So those are our two inputs. And based off of that, we get an output, which is our E. coli level. And anything over 100 is bad. So site 1 on day 1, the E. coli levels are just a little too high for comfort. That's reduced water quality. Okay. Now let's look at table 2. Table 1. Table 1 shows how water quality rating varies with BI. Table 2 shows the average BI of each site during the collection period. Okay, so the higher the BI is, the better your water quality is. Whereas the higher your E. coli is, the worse your water quality is. So that's how we kind of understand our outputs. And then our input is site 1. Our output for BI is 6.3, which would mean it's excellent. Site 2, our input is site 2. On the left side, our output is BI, which is 2.5, which in this case would be fair. Okay. Again, you may not be going through in this level of detail, but you just have to understand what are my inputs and what are my outputs. Okay. And then how they change from figure to graph. So figure 2 shows the water flow at each site on the 5 collection days. So our input is still the days in the site, but our output changes from E. coli to water flow. So that's the difference between these two tables. You'd be surprised, but so often students will miss questions because they just forget which table is measuring which output. And what we see is that site 1 has pretty strong water flow compared to site 2, which is a good thing for water quality. Okay. Question 1, and again, the questions kind of go in order of difficulty. So let's go through the questions and see how we should go about doing them. So if an E. coli level of over 400 colonies formed per 100 milliliters of water is unsafe for swimming, on which of the following collection days and at which site would it have been unsafe to swim? So we just really want to quickly see, we can go one by one on these, or we can just quickly look at, if we're looking at E. coli, we know that we're looking at figure 1, and we can just look at where it's above 400. So if we go to figure 1, the only day above 400 and way above 400 is day 30 at site 1. So day 30, site 1, that's when it would be unsafe to swim because it's well above 400. That's just called a locate data question. The first few are pretty much always locate data, where they just give you your inputs and they want you to figure out what the output would be, or vice versa. Okay. In this case, they told you you have an output above 400, and we just had to find the input. Okay. Based on figures 1 and 2, consider the average water flow and the average E. coli level for site 1 and site 2 over the collection period. Which site had the higher average water flow and which site had the higher average E. coli level? Okay, so it's asking us a lot at once, but again, it's just locating data. And for these, I figured let's just do half of it at a time. So let's just go to figure 2 for water flow and see which one has the higher water flow of the two sites. So if we go to figure 2, site 1 throughout figure 2 always has the higher water flow, right? The black bar is always higher than the gray bar. So higher water flow is definitely going to be site 2, so we can get rid of these two. And then which site has a higher E. coli level? If we go to this figure, figure 1, it's also the black bar. The black bar tends to always be the higher E. coli level. So it's going to be J on this one. Awesome. All right. Sorry, just taking a quick look at my notes. Something is a little off there. Anyway, we'll go on with this. Or hold on. Let me make sure I didn't screw this up. Based on figures 1 and 2, consider the average water level and the average E. coli level for sites 1 and 2 over the collection period. Which site had the higher average water flow? Higher average water flow is definitely site 1. Oh, yeah, I did screw that up. Sorry, it's site 1 and site 1. Site 1 has a higher average water flow, and site 1 has a higher average E. coli level. So if you were shouting at the screen, correctly so. Site 1 and site 1. So higher average water flow, you can get rid of those two. And then again, you get rid of this one for that one. So yeah, F is correct for 2. All right. According to table 1, what is the relationship between water quality and biotic index? So this is really straightforward. The higher the BI, the better your water quality. So as water quality improves, biotic index increases. That looks right to me. As water quality improves, BI remains the same. No. As water quality degrades, biotic index increases. No, that's the opposite of A. As water and then remains the same. No. So that one's definitely A. Okay. 4. As water quality improves, the number of stonefly larvae, a type of aquatic invertebrate, increases. So better water quality means more of this particular animal. Students hypothesized that more stonefly larvae would be found at site 1 than at site 2. Are the data presented in table 2 consistent with this hypothesis? So a mouthful here, but if we just break down what it's actually asking, it's fairly straightforward. So essentially, students are hypothesizing that there are more stonefly larvae at site 1. So they're just saying, does site 1, according to table 2, have the better water quality? Because more stonefly larvae means better water quality. So let's go to table 2 and see if site 1 has the better water quality. So table 2, sure enough, site 1 has a better water quality. So their hypothesis is, or their assertion is supported, right? Because higher BI means better water quality. So F is yes. So we know it's not enough. So yes, based on BI, site 1 had a water quality rating of good, and site 2 had a water quality rating of poor. Actually, no, we know that 6.3 is well above excellent. So immediately we know we can get rid of that one. Yes, based on BI, Site 1 had a water quality rating of excellent, and Site 2 had a water quality rating of fair. And you can go back and double check that, but for the sake of moving on, you'll notice that Site 2 does have fair, within the range of fair. All right, 5. Which set of data best supports the claim that Site 1 has lower water quality than Site 2? And they even put it in italics, so we have to be careful here. Okay, so we need to know what's going to show us Site 1 having lower water quality. Well, really, it's just going to be this figure 1, because figure 1 shows that Site 1 has higher E. coli throughout, which is a bad thing. If we look at table 1 doesn't compare the sites, so immediately we know it's not table 1 because there's no comparison. Table 2 shows Site 1 is having a higher BI, so that's a good thing. So, and then figure 2 shows a higher water flow for Site 1, which is a good thing. So essentially, it's figure 1. Figure 1 shows higher E. coli levels for Site 1, which is a bad thing. So figure 1 shows lower water quality. If we just looked at figure 1 in isolation, we would think that Site 1 has lower water quality. Okay, 6, which should be the hardest one of the bunch. They're supposed to get more difficult as we go up in number. Okay. So suppose, so this is probably a suppose most likely question, and it is, which means that they never actually measured it. If you get a suppose most likely, it's not measured, you're going to have to make an inference based off of the data you've been given. So suppose large amounts of fertilizer from adjacent fields began to enter the river at Site 1. So that's probably a bad thing. You probably don't want a lot of fertilizer entering a river. A little bit of background knowledge. The BI of this site will most likely change in which of the following ways. Okay, so I don't know if you have the basic environmental science background, but a lot of runoff going into a river is a bad thing. It causes algal blooms. It hurts the biodiversity of the lake or the river. It's not a good thing to get all types of fertilizer running off into a river or lake. It disturbs the ecosystem. So the BI is going to go down. The water quality is going to go down. So BI is not going to increase. It's going to decrease because water quality is likely to decrease. So that one's going to be J. Okay. So far, if that's helpful, you can stop the video here and you don't have to watch any more. We're just going to do one more together in case you want to kind of hang out and get more practice with me. So we'll just do one more of kind of comparing experiments. And that's passage 2. Okay. So let's just kind of hop right into it. And again, don't feel like you need to do this, but if you want extra practice, I'm here for you. All right. Okay, so passage 2. So let's figure out what's going on. Aluminum water-based paints, AWPs, contain aluminum AL flakes that give surfaces a shiny metallic appearance. If the flakes corrode, a dull coating of aluminum hydroxide forms on them, and they give us this chemical conversion. So we have the water and the aluminum. So this is the aluminum water-based paints. And if it erodes, this is kind of the chemical output that we get. So table 1 shows the volume of H2 gas produced over time at 25 degrees Celsius and 1 atmospheric pressure unit for 100 milliliter samples of freshly made AWPs, so aluminum water-based paints. 1 to 3 in 3 separate trials. AWPs 1 to 3 were identical, except each had a different concentration of DMEA, an AWP ingredient that increases pH. So they're saying, hey, look, all of these are the same. Nothing's different except for the pH. They have different levels of DMEA, so they have different pHs. Okay, and we know that the higher the pH you have, the more kind of basic you become, right? And a low pH is acidity. So anyway, let's take a look at this one. So the AWP trial was repeated 4 times. And what we see is right here, what we see is that the higher your pH, so the more kind of basic you are, the more H2 of an output. And that essentially, that H2 output is essentially showing how fast these paints are corroding. So we don't want a high pH if we want the paint to last. Okay, so the AWP3 trial was repeated. So they took kind of the one that corroded the most, and they repeated it 4 times. But for each trial, the sample had the same concentration of 1 of 4 corrosion inhibitors. So in this case, instead of the input being pH and day and then measuring the output of H2, we're still measuring an output of H2, but our input is now just the type of chemical inhibitor that we choose to use. And this just shows how different chemical inhibitors prevent corrosion. And notice that all of these do a better job than no corrosive element if you compare them to AWP3, which is what this one is measuring down here, right? This corrodes a lot faster than it does with the equivalent in the table. And again, you don't need to get that deep, but you need to know that this table is measuring AWP3, and these are your inputs. And your inputs are essentially the corrosive inhibitor and the day, and your output is the volume. Okay, and that's it. We're ready to go into the questions. So number 7, based on table 1, which of the following graphs best shows how the volume of H2 produced by AWP3 changed over time? So we're looking table 1 right here. We're looking AWP2, so this one. And what we see is over time, and let me actually get rid of a lot of the markings here because this could kind of get confusing. But what we see here is that over time, the amount of H2 is increasing, and it seems to be increasing at an increasing amount, but the factor by which it's increasing is leveling off. So let's kind of look at this, and we can even just kind of take points and look, but we know it's not going down. So that gets rid of C, that gets rid of D. And then the question is, how is it going up? Is it A or B? Well, what we notice is with A, it's going up kind of at a faster rate, where B is a bit more gradual. And this, you notice the distance between each of these points, it's going up faster, but we can also just try a point. So we know at day 6, we should get out 461. So an input of 6 on day 6, ooh, no, that's way above. Where an input of 6 on day 6, 461. So actually, it's a good thing we double checked here. A is going to get us the wrong answer if we weren't careful. And then an input of day 4 should get us 187. And that looks about right. Where an input of day 4, we're way too high. Yeah. So this one is definitely B. So it's a good thing we double checked on the points there. Okay. 8. Based on table 1, if the volume of H2 produced by day 10 from the AWP1 sample had been measured, it would most likely, okay, so again, this is a most likely question, meaning that they didn't actually measure day 10. If you look at table 1, we only go up to day 8. We don't have a day 10. But they want us to make an inference. This is a data inference question. So for AWP1, what would H2, what would our output have been if our input was day 10? Well, what we notice is that it would have, we're going up, we're trending up, so we can make an inference that it would be above 133. And it looks like from here to here, we went up roughly about 50, and it looks like we go up roughly about 50 again. So we could assume we're probably going to go up around 50. So G is the answer here. It's going to be greater than 133, but we're very unlikely it's going to go above 461. We would have to go up by, more than 300 to get that, well over 300. Okay, so 9, according to table 1, what volume of H2 was produced by AWP1 from the time the volume was measured on day 6 until the time the volume was measured on day 8? So again, we just have to pin down exactly what this is asking. So it's saying go to table 1, look at AWP1, and compare the output of H2 on day 6 to the output of H2 on day 8. And it wants to know the difference between the two. So if we go table one, day 6 versus day 8 of AWP1, we get 52. 52 is the difference. So from day 6 to day 8, 52 milliliters of H2 were produced. So again, that's just kind of finding what we need on the chart. Okay, number 10. In the trials represented in Table 1 and Figure 1, by measuring the volume of H2, the experiments were able to monitor the rate at which. Okay, so this is kind of asking more of a zoom out. Do you understand this experiment as a whole? And essentially, when we measure H2, we're measuring the rate of corrosion, right? We're measuring how quickly or how much this aluminum water-based paint is changing from aluminum and water to these two compounds. So let's take a look. How quickly H2O is converted to Al? Well, no, because Al is on the left side, not the right, and H2 isn't being converted to that. How quickly Al is converted to H2O? Nope, both of those are on the left side. How quickly Al is converted to AlOH3? Yeah, it would show us how quickly, knowing how much of an output we get of this, we would understand how quickly this is turning into this. But let's just check the last one. Yeah, no, AlOH3 is an output. So yeah, we're just measuring, by measuring how much H2 of an output we have, it also tells us the extent to which this is converting to this. So kind of how quickly our chemical reaction, or to what extent our chemical reaction is occurring. Okay, let's look at 11. Based on the passage, is DMEA most likely an acid or a base? So this just requires a little bit of background knowledge. And you can easily Google this, but pH level of acidity, this is something you want to know anyway. So 7 is neutral. So anything below 7 is acidic. So based on the passage, is DMEA most likely an acid or a base? Well, what we see is we see that DMEA, the more DMA we put in, what happens is our pH increases. So if our pH increases as we put in more DMEA, and all of these pHs, by the way, are basic. But if we input more DMEA and that increases our pH, that means that DMEA is a base because it increases our pH. As your pH goes up, you become more basic. Okay, and 12, which should be the hardest one. So let's take a look at 12 here. Consider the volume of H2 produced by day 2 from AWP3. So we're considering this output on day 2 with these inputs, and then with no corrosion inhibitor. Based on Table 1 and Figure 1, the AWP3 sample containing EDTA produced approximately the same volume of H. Okay, so there's a lot going on here. Let's just break it up into pieces. So they're going to have us use a table and a figure, and we just need to break it up piece by piece. So let's just do the consider part first. So let's go day 2, AWP3, and figure out what H2 output we get. So AWP3, day 2, we get 121 H2. So our H2 is an output of 121, I think it was milligrams, or milliliters, sorry. Okay, so now what it says is the AWP3 sample containing EDTA produced approximately the same amount, so 121, by which of the following days? So let's look up. So this is AWP3 example throughout this trial, and we're looking for EDTA. So we're looking at essentially, we look carefully, it's this line right here, this guy. And we want to know when it gets to 121, by what day. And it looks like around day 10 is when it gets to 121, and then it kind of levels off. So there we go. And if we wanted to double check, day 7, yeah, we're below 100. So it's definitely going to be day 10. Anyway, good thing we caught the mistake, or I caught the mistake. I think you probably already knew it was a mistake on number 7. But anyway, hopefully this helps kind of provide a framework for exactly how you want to go through these. Again, obviously you're not going to do it as slowly as I did it in this video. This video is more for instructional purposes, but hopefully this kind of provides a format of how to process these questions. There's going to be one more science video. It's going to be the 403 video in which we look at the competing hypotheses and how to go about doing that. Okay, anyway, good luck, and hopefully I'll see you back for more tutorial videos.